I'll start by discussing two algorithms which construct a spanning tree for a given graph. And the first one is called the depth-first search. Depth-first search algorithm. So it proceeds in the following way. We first choose a route, and then from the route we form a path by adding edges successively and not forming a circuit. So from the route, form a path by adding edges successively, not forming a circuit. Well, of course, I mean a simple circuit. So a path will look something like this. So we start from the root, and then we add one edge, and then to that new vertex we add another edge, and so on. If that is not possible, which can happen if whatever choices you get will result in having a simple circuit. So if that's not possible, what we do, we backtrack along the path and try to start out a new path. If that is not possible, backtrack and start a new path. And then build that new path as long as possible. If not possible, backtrack and always check for possibilities of new paths. So that's the key idea, but it doesn't give you a prescription for unique choices. So to have such a prescription, which is conventional, we're going to look at graphs for which each vertex comes with a numerical label. And then whenever we have choices, we'll give vertices with smaller labels preference over other vertices. Right? So we will work with graphs for which each vertex has a numerical label. It's just a convention, right? There's no special meaning to these labels. And then we will give preference to vertices with smaller labels whenever a choice arises. I'm not sure I spelled arise correctly. Please forgive my spelling mistakes. I'm not good at it. But, any objections? Arises? Looks okay? Sorry. Right. So I'm going to illustrate this on a concrete graph. So here you see each vertex is labeled by an integer, right? So whenever I will have a choice, I will go for vertices with smallest labels available. But this is just a convention, you know. In practice, narrowing down your choices, right, depends on the context. So we choose a root, and I will choose the root to be the vertex with the smallest label. So that's 1, label the vertex with label 1. And I'll be, so as I go, as I make my choices, I will label them on the drawing, and also separately will be drawing my tree. Right? So I continue with this strategy of building long paths, and if not possible backtracking, building more long paths, until each vertex of this graph will be in my tree. So if I'm at 1, I can now add to the vertex 5, 3, 6, or 9. So I have 4 possible choices for the first edge, and I'll go for 3 because that has the smallest label. So that's the beginning of my tree, and I mark it on the graph. Well, while at 3, I try now to add a new vertex, and from 3 I can either go to 2 or can go to 4. I can go back to 1, but I don't want to do that because that will create a circuit. You know, always remember that whenever we add new vertices, we check that no circuits are created. So I go to 2 because it has smaller label than 4. Mark that on the graph. From 2, I can only go to 5, right? There is no other choice available. And now, while at 5, I'm stuck, right? That's the first time I got stuck because from 5, the only new edge available will be from 5, 1, but that will get me back to 1 and that will create a simple circuit. I don't want to do that, so I start backtracking. So I go back to 2 and check, and there I don't find any new possibilities. So I backtrack further back to 3, and here I find just one new possibility. I can go now to 4. So I backtrack to 3, and now I'm able to start out a new path going to 4. Right, so that branches off on my spanning tree. So from 4 I can only go to 6. So I add 6 to my spanning tree. From 6, well, again, I don't want to go back to 1. I can go either to 7 or to 10. Since we agreed to give preference to smaller labels, I go to 7. Okay. Next, from 7 I can only go to 10. Right? From 10 I can only go back to 9. That's the only new vertex available. From 10 to 9. From 9 I can go either to 8 or to 11. 8 has a smaller label, so I go to 8. And you can see I'm stuck again. So let's just add this vertex 8. So I cannot go any further, so I start backtracking. I backtrack back to 9. And well, I don't want to go back to 1, so I branch off to 11 from 9. So when I draw it, it's just a matter of convenience, or how you draw it doesn't really matter. So I go from 9 to 11. Right, and from 11 I can only go to 12. And then I happily stop because now all vertices are in my tree. Okay, so let's just write about this. This was an example for a depth first search algorithm. Okay. So it produces rather long trees with not that many branchings. If I started from some other vertex or modified the rule for, say, giving preference not to smaller vertices but to larger vertices, chances are the same strategy would have created a different depth search, different spanning tree, right? So which tree exactly is produced by the strategy depends really on the conventions, right, and the starting point. Any questions about this algorithm? Okay. Then let's discuss another strategy, which is called the breadth first search. Breadth first search algorithm. So here from the start I will assume that I have labels assigned to my vertices, and these labels, they provide an ordering for vertices, right, from smaller to larger ones. So again, I choose a root, let's say the vertex with the smallest label. For example, the vertex with the smallest label. And then I add to my tree all vertices adjacent to the root. So add to the tree all vertices adjacent to the root, which means all vertices linked by a single edge. So this is my root. I take immediately all possible branchings, right? And this creates level 1 vertices of descendants. Then I use the ordering on these level 1 vertices provided by the labels, and I inspect them in that order, starting with the smallest label available, and try to add level 2 vertices, again, as many as possible. So then inspect the level 1 vertices following the order given by the labels. Add all possible level 2 vertices, not creating simple circuits. Continue to the next level. Stop when all vertices are in the tree. Okay, let me illustrate how this works on the same graph, which I looked at before. Let's just go to breadth first. Search algorithm. Again, I'll start with 1. And now the beginning is different. I will add all adjacent vertices to the 1, and I'll be marking the new edges I'm choosing on the drawing. And well, it helps if you can keep arranging them in the order of increasing labels. So I add here 3, 5, 6, and 9. 5, 6, 9. Alright, so I took immediately all possible branchings. So this created for me 4 level 1 vertices. And now I start adding level 2 vertices. And I'll start adding them to with vertex 3, because that has the smallest label. So to 3 I can add 2 and 4. And 4. So I'm done. I cannot add anything more to 3, so I go next to 5. And to 5, I could have added 2, but not anymore, because 2 is already in my tree, so that would create a circuit. So I'm not doing that, so nothing can be added to 5. And next, I'm passing on to 6. I cannot add 4, because again, that would create a circuit, but I can add 7 and 10. So I do that. So that's 7. And that's, sorry, I should have added it to 6. Yeah, nothing can be added to 5, but to 6 we add 7. Okay, and finally, the last level 1 vertex is 9, and at this stage I can only add 8 to it, and 11. So 8 and 11, because 10 is already in the tree. So 8 and 11, and I'm done now, right? Because I've added all possible level 2 vertices. And now I repeat these steps. So I choose the smallest label available amongst the level 2 vertices. So that's vertex 2. Right, and nothing can be added to it. The next one is label 4. Again, nothing can be added. 7. Nothing can be added. 10. Nothing. 8, nothing. So you can see, actually, just examining the graph, you can see that 12 is the only missing vertex from the tree. So my only possibility to add a vertex is when inspecting vertex 11. So I finish off by adding a single level 3 vertex with label 12. And I mark it on the graph as well. Marking on the graph helps to kind of making sure that all vertices are there. And also, you can see your available connections. But the final result is drawn separately, so that's our spanning tree. Any questions on this algorithm? All clear? Yeah. Okay. Yeah. So. They have many applications in data storage, and in particular the depth first is used by internet spiders or crawlers which index all the websites. Okay, so let's move on and discuss minimal spanning trees. So this will be done in the context of weighted graphs. Minimal or minimum spanning trees. So let capital G be a weighted graph. So this means, like in the case of Dijkstra's algorithm, that each edge is equipped with a number called its weight. And again, we'll be looking at the situations with non-negative weights. So weighted graph with non-negative weights. A minimum spanning tree with a special property that it has the smallest possible total weight is called a minimal tree. So let's write this down. A minimal spanning tree, T, is a spanning tree that has the smallest possible total weight. So this total weight we'll denote as W of T, so T stands for the tree, W for its total weight, and we can write it as a sum, so we use the summation symbol, which runs over all edges belonging to our tree, and we're summing the weights of these edges. So this places an additional constraint on the spanning tree, so there can be several spanning trees, and we've seen examples, typically there are many for a graph. And if you have a weighted graph, then you can try to select the one with the minimal total weight. Again, it might not be unique, right? So there might be several minimal spanning trees. You don't know, that depends on the graph. But that's a very important problem in applications. So this additional constraint arises naturally in various applications. For example, if you want to build a road network which would connect certain nodes, you might want to have the total length as small as possible, right? So the minimum of the weight could be distance between your towns, or it could be related to costs, right? If you want to minimize the cost of building such a network, then each connection will be assigned a certain cost. And if you linked up all of the nodes using a spanning tree, you may want to minimize then the total cost, right? And there are nice algorithms which allow you to find such minimal spanning trees. And so we will look into two such algorithms. They're named after people who invented them. And the first algorithm I'll discuss is called Prim's algorithm. Named after the inventor. The surname was Prim. So we start by picking any edge with the smallest weight. There might be a unique one, or there might be several smallest weights available, then we just pick any. And then we add that edge to our tree. Then we continue by adding edges of minimum weight available that are linked to a vertex already in the tree. Okay? And making sure we're not creating any simple circuits. We stop when all vertices are in the tree. So let's write this down. So start by picking any edge with the smallest weight. Continue by adding edges of minimum weight available that are linked to a vertex already in our tree. And making sure no simple circuits are created. Inspecting all these numbers, which are all the weights, you see that there's a unique one, the HDE, which has weight 1. So first choice is therefore the HDE, which has weight 1. And I also mark this on the graph itself. So next, we're supposed to add another vertex which is linked to this HDE. So I can either add B or F or I or H, G, A, pretty much any other vertex, as it turns out. And I should make sure among all of those possibilities I choose the one with the smallest weight available, which again there might be many. And one useful strategy is actually by scanning, for small graphs you can just scan visually all the weights which are sitting there and see which one is the smallest one available after the weight 1. So you see there are no 2's here, so the next available weight will be 3. And then after that you can check whether you can link it to E or D. So we either can go ahead and add vertex BE, so BE would be weight 3, or H, right? Because that would be linked by DH. So anyone is okay, right? The trees might look, well, the final trees we construct, might depend on these choices, but it's guaranteed that each one of these trees will be minimal spanning trees. So their total weight should be independent of all of these choices. Okay, so I here will choose B. So that's adding EB with weight 3. And that didn't change my options in terms of weight 3. So next step, I must add DH, because it's the smallest weight I can add to the tree. So DH is weight 3 as well. So there are 2 more 3's, CF and FI on the graph. But those would not be linked to the tree. So at each step in Prim's algorithm, I'm growing a tree, right? So I should, each new vertex should be linked to the previously chosen ones. So those are not an option then, CF and CI. Then I should check whether I can add weight 4 vertices, right? Weight 4 edges. So EH is such an edge, but that would create a simple circuit. So this triangle would be a simple circuit. And that's the only weight 4 in the graph. So next I pass to weight 5. Here I have various options. I can add EA, so this is weight 5, or I can add BF, which is weight 5, or EF, or EI. Each of these choices is legitimate, right? So I'm guaranteed whichever choice I make, it will be a minimal spanning tree. So let me choose BF. So BF, weight 5. And now that actually, I didn't think of it in advance, but that made the weight 3 available. So the algorithm doesn't tell you that you should look, at expanding your options. No, all the instructions are there. But by accident, I got now this weight 3 edges available, CF and FI. So I proceed by adding those. So now I must add them because that's the smallest weight available. So So let's add CF. It's weight 3. And next I add FI, which is weight 3 as well. Okay. So I'm done with weight 3. Weight 4 was never possible. Is not possible. I'm back to weight 5. So let's see what weight 5s I can add. I cannot add EI because that will create a simple circuit, but I can still add either BA or EA. Let's just pick one of them at random. Say AB. 5. So now EA is no longer possible, so nothing of weight 5 can be added. So I try to see if weight 6 is a possibility. So know that those will create simple circuits. So adding BC will create a simple circuit, and adding AD creates a simple circuit. So next best option is weight 7, and that leads me to my final edge, DG, which is weight 7. Okay, so now I know that I have enough edges, and on the graph I see that it's a tree, there are no simple circuits. So we can now calculate the total weight just by adding all of these numbers. So that gives me 4 plus 9, sorry, plus 8, plus 6, plus 12, so it's 10, plus 20, yeah, so 10 plus 20, that's 30. So this number is actually independent of any choices which we made. Right? So that's the minimal possible total weight. It's guaranteed by the algorithm. Okay, so we can write that W mean, the minimal weight of the spanning tree, is equal to 30. Any questions about Prim's algorithm? Makes sense? Everybody? Okay, then I'll discuss different algorithms. Oh, better. So next algorithm we're going to discuss is called Kruskal's algorithm. Kruskal is not a person. And here you follow the same set of instructions as in Prim's algorithm, except for you no longer care about each new vertex being adjacent to a vertex already in the tree. And so we just choose an edge with minimal weight. And then successively add edges with the minimal weight available that do not form, that do not result in having a simple circuit. That do not result in having a simple circuit. Stop when all vertices are in the tree. So we just dropped the condition that we have to have a tree at each step. So what happens, you can start picking edges in different parts of the graph. And initially, you'll have them disconnected. But as you're picking more and more edges, they start linking up and start forming a tree. Right? And so what can be said actually about this algorithm is that the weights we're choosing will be always monotonically increasing. So we will exhaust all possible smallest weights, and then next to smallest weights, and so on. So if this is the weight of the first edge chosen, W of E1, that will be smaller or equal than the weight of the edge E2, that will be smaller or equal than the weight of the edge E3, and so on. That was not necessarily the case in Prim's algorithm because we were additionally constrained by having by the condition that all new edges must be incident to a vertex already in the tree, so that sometimes we wouldn't have the smallest weight available because of that condition. That would arrive later. Right? But here, definitely, they will form such a monotonically increasing or non-decreasing sequence. So let me take the same graph and illustrate how this algorithm works. So, Kruskos algorithm. So I will arrange it in the same way as a table. Choice, edge, and weight. And since it's the same graph, there have to be 8 edges chosen. Okay, and we start out with the minimal weight available, which is dE, as before, weight 1. And then the next smallest weight available is 3, and we can start picking weight 3 edges wherever they are in the graph. They don't have to be linked. For example, as my next choice, I can pick CF, weight 3, and pick, well, BE. As long as I'm not forming simple circuits, that's fine. Each choice is fine. So weight 3, FI, weight 3, DH, weight 3, and I'm done with all weight 3 edges. Right, so now proceed to weight 4, which is again a single edge EH, and I cannot add it because that would form a simple circuit. So we'll move on to weight 5, and again we can pick them at random as long as we not form a simple circuit. So let's take EF, weight 5, AE, weight 5, and nothing else can be added because it would form simple circuits. Nothing, weight 6 can be added either. So 7 is our next best option, but HI as weight 7 cannot be added. That will form a simple circuit. So we go for DG of weight 7, and that completes our spanning tree. Let's check ourselves what the total weight. It should come out to be exactly the same that we found in Prim's algorithm, provided we executed both algorithms correctly. So it's a check of both of them. So 3 times 4, that's 12, that's 17, and that's 1. So W mean of this T, call it T dash to distinguish it from the one produced by Prim's algorithm. So that's 1 plus 12 plus 17, which again is equal to 30, same number, right? Although the tree came out different. Okay. Any questions about Kruskal's? Sorry? Yeah, I'm going to discuss this next, Yeah. Anything about the executing the algorithms before that? Yes. Is the weight again, please? Exactly, yes. For the same graph, it should be the same number. So it doesn't depend on the choices, because the algorithm guarantees to produce minimal total weight available. For this graph, yes. Yeah. So for some other graph, it could be 100, but all variations we have within Prim's algorithm or within Kruskal's algorithms should be essential for the total weight. It could be different spanning trees, but they're guaranteed to be of minimal weight, and its minimum is minimum, right? It's a single number. Right, so I have two algorithms. Kruskal looks easier, doesn't it, right? Because you just grab your minimal weight available wherever it is, and then you stop when you cannot, when all the vertices are there. In fact, both algorithms are following this strategy of they fall into this class of greedy algorithms. So both, just want to make a note, these are both Prim's and Kruskal's are examples of greedy algorithms like Discrete, which we studied before. So we want to minimize our total weight. So at each iteration, we follow our grid and we go for the best option available at that stage. And we're not worrying about how our earlier choices will affect our future choices, right? It's not obvious that it works, but on the next lecture, I will prove for you Prim's algorithm, just as a sample proof. It's the only time I'll be proving an algorithm in this course, but you'll see that indeed, it will prove without doubt that this algorithm provides a minimal spanning tree. But so both are greedy algorithms, and as I said, Kruskal's may look simpler, but this is really a false impression due to looking at small graphs, right? So I've drawn a small graph, and it's easy to scan it to find the minimal weights. But imagine that you had a huge graph with thousands or millions of vertices and edges, then Kruskal's would be in trouble, because to find your next available option, you have to scan the entire graph, right? While with Prim's algorithm, you only have to scan the neighborhood of your current tree, right? Whatever you can add to what you already have, and that can be a much smaller number of edges. So depending on how many edges you have in the graph, either Prim's or Kruskal's can be more advantageous. And in fact, one can prove the following estimate for a number of operations. So the number of operations to find a minimal spanning tree in a graph with this many vertices and this many edges is approximately the number of edges times the logarithm of the number of edges in Kruskal's algorithm and it's the number of edges times the logarithm of the number of vertices in Prim's algorithm. It is hard work to find these estimates, so I don't have any intuitive explanation of where the logarithms come from. So it's really hard work, but this can be shown. And you see that while Kruskal's is only really sensitive to the numbers of edges, Prim's is sensitive to the number of vertices in your graph as well. So Kruskal's would work faster for what is called sparse graphs, for which there are lots of vertices and few edges. So Kruskal's works faster than Prim's in so-called sparse graphs. So the sparse graphs are the graphs in which the number of edges is much smaller than the square of the vertices. So why the square? Because in a simple graph we can have an easy estimate on the number of edges given the number of vertices. Right? So if you link up all pairs of vertices, like in the complete graph about which we talked on the last lecture, then at most you can get the number of vertices times the number of vertices minus 1 divided by 2, which is the binomial coefficient. And that roughly goes as the square of the number of vertices. If you, so sparse graph is the graph for which the number of edges is actually much smaller than that. So you have few possible edges in your graph. And just the last remark, Prim's algorithm works faster if we have lots of edges. Works faster if we have lots of edges, so of the order of number of vertices squared. So if you have 100 vertices and the number of edges is in the thousands, then Prim's will work faster. If its number of edges is in the hundreds as well, then Kruskal's will work faster. So hopefully that answers the question you had before. Okay, that's all for today.